In this lecture, we will address important issue that is of practical relevance. Okay, so this is about efficiency in energy engineering. We'll differentiate between two types of efficiency. For most of the lecture, we'll be looking at a practical definition of efficiency. So in an earlier lecture, what did we do? We completed the introduction to first law of thermodynamics. This involved generalizing work energy theorem and conservation of energy from mechanics to a broader range of conditions. That's what thermodynamics is about. It incorporates the definition of temperature and so on. Okay, so we completed that introduction. So this is the mathematical expression of the first law. If you look at the history of thermodynamics, much of the foundations of thermodynamics was brought out under very practical consideration. People were trying to ask questions like how much of work can be obtained by burning certain amount of coal. Okay, so things like this. So this efficiency, issues of efficiency, what is the maximum output of work that can be obtained, that has always been central to thermodynamics. Okay, so it has a very practical outlook. So that's why it's so important in most branches of engineering. So this practical efficiency, that's a differentiate between conceptual efficiency and practical efficiency. Practical efficiency is desired output by required input. Okay, so you would often see data like this. Okay, so gas-driven heater. Okay, so here what is this? A water heater. So desired output is just temperature rise of water. Okay, that's what a water heater does, right? And you would see data like this, conventional efficiency and high efficiency. So actually, if you see the difference, this is because of just insulation. Okay, same thing here, electrical and conventional high efficiency. The better the insulation, lesser is the heat that escapes out of the heater. So it's more efficient. Okay, so this way of controlling efficiency. Okay, so at the bottom, when you say required input is the amount of heat that can be obtained by burning gas, certain amount of gas, or the ohmic heat that can be generated. Okay, by supplying current at a particular potential and so on. Okay, so that's what goes at the bottom. Okay, see, this is fairly. This is nothing to do almost with the fundamental limitations you will see from second law of thermodynamics. Okay, these are all practical and useful measures of efficiency. We will a lot of it you will see a lot of energy conversion devices. For example, if you think about light bulb. Okay, so what is happening here? You are converting again an electrical input to an light output. Okay, so there are different kinds of light output you can get from different sources by just generating fire. Okay, incandescent Edisonian bulb, then CFL and so on. Okay, solid state light emitting diode bulb. Okay, so all these things are different ways of generating light. There you ask the question, what is the desired output is amount of light that can be obtained, measured in lumens. Okay, and the electrical energy, electrical power that goes into generating that particular light. Okay, so this is something you ought to be aware of. Okay, so what is the efficiency of different sources? As you can see here, fire is very low. One of the reasons why incandescent bulb is being eliminated is because the efficiencies are quite low. Okay, so as compared to modern CFL, okay, and so on. Okay, so that's much better. Okay, and this you must be aware of these numbers. But in this course, we are not going to analyze these numbers. Okay, so most of the analysis we'll be doing will be with respect to thermodynamics, and a related subject close related to thermodynamics is heat transfer. But there, at least you might be doing some more analysis on why certain energy conversion is more efficient. For example, here there's an electrical a stove which is heating, let's say a soup, some part of the heat is it escapes to the atmosphere. Okay, so what with heat transfer methods you use for analyzing heat transfer problem can be used for analyzing these kinds of energy conversion devices. Okay, so again, this is not something we are going to be analyzing in this course, but you should be aware of certain forms of efficiency in energy conversion device and associated issues like what is the environmental cost of energy conversion. Okay, so so whether this is a very, very current topic. Okay, people are trying to eliminate coal and move on to natural gas. Okay, because the amount of CO2 that is generated is lesser. Even better is using renewable energies. Okay, so these kinds of issues you should be, though not central to this course on thermodynamics, it's a peripheral topic, but it's a very, very important topic, very relevant to engineering. So, for example, you might have seen, if you're in campus, you would have seen electric rickshaws. Okay, so here the discussion can be that whether electrical rickshaws are going to decrease pollution. Okay, so if you ask such a question, so the answer to this depends very much on what is the way you're going to charge the battery that go into e-rickshaw. Okay, supposing the electrical power that is used for charging the battery comes from a coal power plant. In fact, that is not very efficient in the sense that you are converting the coal power or a natural gas power to charge a battery, and then which is used for running a rickshaw. Okay, but however, if this battery is charged from a solar source or renewable energy source like a windmill or a solar farm, then it can be very efficient. Okay, so but even with despite such issues, e-auto rickshaws, rickshaws are electric vehicles are used because at least you can localize the pollution in the sense that most of the CO2 that is being generated is around the power plant. Maybe CO2 can be captured around the power plant compared to CO2 generation across the atmosphere. Okay, so there are lots of these issues that are there. These are all not topics central to thermodynamics, but as engineers, you should be informed about these issues. Your textbook sort of mentions some such issues. Okay, so it talks about pollution that is there from a hydrocarbon-driven power plant, how the pollutants that are generated photochemically are converted to other components, other chemicals, pollutants, which generate acid rains. And then there can be photochemical generation of ozone, which can combine with cloud and form smog. These are all extremely important issues in engineering, but you should, the book has a qualitative discussion on these issues. You should go over this as it's important to be informed about such issues, even though we are not going to dwell into these issues in greater detail. There is a conceptual issue with respect to heating values of fuel. So here I will elaborate this issue. So here there is a hydrocarbon which is mixed with gas and combustion. Okay, so heat is generated, and the products of this combustion is CO2, H2O, and N2. Okay, this N2 comes from air. Okay, so here what is the output? The amount of heat released during combustion is your output. Okay, so what is the input? Heating value of the fuel burn. So you will hear two kinds of heating value. One is called lower heating value. Another is called higher heating value. So what is the difference here? So when water, that is H2O, that is being generated, escapes out as water vapor. Okay, so that's what is used for defining the lower heating value. Okay, however, if this water vapor can be condensed, okay, so when you form liquid water, there are bonds that are formed that will liberate some more heat. Okay, so that can also be used for your particular purpose. Okay, so that certain more processing needs to be done. So, but that is very useful if you can capture. See, these two are not condensable gases. Okay, CO2 and N2 are not condensable, not easily condensable gases. However, H2O is an easily condensable, relatively easy to condense gas. So when such condensation occurs, heat can be generated, which results in lower, results in the generation of lower heating value, difference in lower heating value and higher heating value. So this is a conceptual point you should be aware of. And there are other measures of efficiency. For example, here we have a fan. So what does a fan do? You get in some air, for example, and the incoming air is more or less at zero velocities. Okay, approximately the center of mass here is moving at very low velocities. It can be approximated to be zero. Okay, so the kinetic energy of the incoming gas is zero, but it is accelerated to a particular velocity, let's say. So the kinetic energy of the center of mass increases. The potential energy, there's not much change. Everything is under atmospheric pressure. So just the energy output, okay, in terms of this air is just the kinetic energy, okay. So that is, this kinetic energy is generated using an electrical output, okay, electrical input, okay. So so you can compute the efficiency of this device, okay. So much of the efficiency is not one, because there are a lot of frictional losses, okay, because of the rotation of the rotor, and there are other dissipative losses, but the efficiency is still fairly high, okay. So many other equipments, okay, so which you see in power devices can be analyzed in a similar manner. For example, here, eventually you want to generate electrical power via a generator. Here the output is work output. To get this, you're moving a shaft, which can be, this movement of the shaft can be due to a turbine. Okay, so you can break down the efficiency into two parts. Okay, the combined efficiency of a turbine and a generator can be broken down to efficiency of the turbine and then efficiency of the generator. Okay, so how does the turbine, let's say, rotates this shaft? Okay, so how does that shaft output? Okay, so the work rate of work generation via the shaft is because of slowing down of a fluid. Okay, so the mechanical energy loss in a fluid gives rise to this work or power output. Okay, so the turbine efficiency can be obtained using this power generated in the shaft, rotation of the shaft, and mechanical energy loss, okay, per unit time. In this generator, the electrical output is the power, and the shaft, the work, the power of the shaft, okay, that is the input, okay. So both these things, when combined together, is going to be giving the efficiency of the turbine and generator put together, okay. So you multiply and you can get a quantitative expression for such a device, okay. So all these things are can be easily analyzed, and it's important to look at these numbers, okay, just so that you have a quantitative feel. In engineering, it's very important to have a feel for these numbers, okay. So even though this is not very central to thermodynamics, okay, but this is a topic that you should be aware of, and the book does a bit of discussion on these topics. Another important area of a lot of contemporary interest is what are the upper bounds of efficiency or energy conversion you can get from variety of devices. For example, if you have a solar power, okay, solar cell, what is the maximum efficiency, okay, that you can get from a solar cell. It's called a Shockley quasar limit. So this depends upon the input energy is the black body radiation of the sun, and the output power depends upon the band gap of a semiconductor. I think Shockley and Quasar, they analyzed this for the first time for silicon, I guess. Okay, so there's a bound beyond which we cannot go. Okay, so it is very important to have a very conceptual analysis of what are the bounds of energy conversion that you can get. Okay, for example, solar energy to power output from a solar cell. Okay, so likewise, you can get what are the bounds that you can get from a turbine, okay, depending upon the wingspan, the height of the wind turbine, and so on. Okay, so we are not going to do all these things, but there are a lot of courses in the institute that look at these kinds of issues. Okay, so here this is a solar farm and this is a wind farm. Okay, so why do we use a farm? It is sort of indicative of what is the power you can get from these kinds of renewable energy technologies. Okay, so these are what are called large area devices. Okay, so these are not solar energy itself is a diffuse energy source. You get on a hot day at around 12 noon, you get about 1 kilowatt per meter squared. Okay, that is the energy input, what is called solar insolation. Okay, so and then this 1 kilowatt, which is approximately power input for an air conditioner. Okay, so for one air conditioner, it's about 1 kilowatt. But not all of the solar energy that is input on the ground can be converted. Okay, so if you take an Amorphous solar cell, the efficiency is only 10%. Okay, so you use a solar farm or a wind farm because you need a lot of land to capture solar energy. Okay, so that is the disadvantage. Okay, so compared to nuclear, okay, so nuclear is highly dense, okay, but it has its own safety issues, but it's not that unsafe. Okay, so there's a perception associated with nuclear technologies. But if you look at historical data, nuclear technologies, nuclear energy is not that unsafe. Okay, so but the advantage of nuclear technology is highly dense. Okay, but solar and wind is not that dense. It's diffuse. This is operational only during daytime. That wind doesn't have such a limitation, but it has other issues associated with it. But you should be, as engineers, you should be as applied scientists and engineers, you should be informed about these issues, even though we are not going to be dealing with such issues in thermodynamics. However, all these issues I'm putting under practical efficiency limits. Okay, so friction, all these things are practical. This is again conceptual. Okay, efficiency limit is conceptual, but an issue which we will be looking at in greater detail. Okay, once we introduce the second law of thermodynamics, is the inherent limitation of heat to work conversion. Okay, so even though heat and work both are useful for increasing the internal energy of the system, in some way they are equivalent, right? They are both internal energy in transit. Okay, that is the similarity, but they are not just equivalent. Okay, so in some ways work is of greater quality, okay, compared to heat. All these things will be brought out when we discuss second law of thermodynamics. This is called the Carnot limitation. Okay, this is probably the climax of the course. Okay, so second law of thermodynamics and what does entropy mean? Okay, so that's the climax of the course, and that has very practical implications. Okay, for all the energy conversion device. That's we'll do about it 2 weeks from now. We'll start second law of thermodynamics. So it's also important to understand that there are energy conversion devices that do not have this Carnot limitation. Okay, so there's a lot of interest in electrochemical energy conversion devices like fuel cells and batteries that do not have Carnot limitations. So an important conceptual theme that you should take home from this course is why are some energy conversion devices limited by Carnot, but why are some other energy conversion devices like fuel cells and batteries are not limited by Carnot? Okay, so and there are fuel cells, high temperature fuel cells, solid oxide fuel cell. The input for this hydrogen and oxygen, and the output is H2O. Okay, so there's no pollution. They operate at very high temperature, and the high temperature water vapor that is generated, if combined with turbine, the efficiency is about more than 90%. Okay, this is remarkable. If you look at the efficiency of thermal power plant, it is about, let's say, 40%. Okay, there are lots of efficiency measures. We'll look at it. Okay, what exactly we mean by efficiency in those cases? It's more conceptual than looking at practical efficiency measures. There'll be exergy efficiency and so on. We'll study such efficiency measures in great depth because they are central to thermodynamics. And along the way, we will also look at why electrochemical energy conversion devices are not limited by Carnot. Okay, so this is something you should be informed. Okay, so these are all contemporary topics of interest. So we will look at this in the next couple of weeks and so on. With that, I will stop this lecture. Thank you.